Hi, welcome back to the Engineering 255 Engineering Statics. In this episode, we're going to continue the discussion of the Chapter 2 Force Vectors. We will focus on the 2.5 and 2.6, which are an extension from the two-dimensional to three-dimensional. In the previous video, we show you how to do the operation if you want to find the resultant force of 2 or 3 or more in the coplanar situation, which is two-dimension. But in more general situation, your force can be three-dimension. So we're going to look at how we do that. It's a very simple and very similar to the previous vector operation. So the objectives of this video is to show you how to represent a three-dimensional vector in the Cartesian coordinate system, and that is x, y, and z. How do you find the magnitude and coordinate angles of a three-dimensional vector? In this angle, we are going to have the angle between x and y and z, and also x and z. And how do you add vectors, especially for the forces in three-dimensional space? Just give you an idea why we do this. Think about this situation. We have a radio tower with the three cables try to stabilize this tower. And each one of the cable are connect to different location. And in this case is location A and B and C. And you can see the distance from the origin, which is the O, has all different dimension. The magnitude is also different. How do you sum them together? And that is the question that we try to resolve, and you have to use the idea that we give you in this chapters. So first, we need to know how we represent a vectors in three dimension in Cartesian. We said that we have a unit vector, which simply is the vector to represent its direction. In the previous case, we showed the I and J represent the unit vector at the x and y direction. Now we add additional one, which is the z direction. We can represent z direction unit vector as the k, which is this one right here. And we do the same thing, and we simply just need to know how we decompose one into three components. The unit vector you need to know is that this unit vector has a magnitude is 1. It's a vector, so you have magnitude. You also have a direction, where the direction is going to be the direction of our axis. It doesn't have a dimension. A unit vector is a vector, but it doesn't have dimension, meaning it doesn't have like a force like a Newton or a meter. No, it just simply helps you to identify the direction. So I, J, K are unit vector in our Cartesian axis. Now, let's assume that we have a vector of A. It is coming from this origin point and point to this position at here. You can find out the dimension from this AX, AY, and AZ. So the AZ is the height, the AYAX are the distance away from the base of this origin. We represent the vector in Cartesian with this way: AX, AY, AZ as the component I, J, and K represent their direction in the axis. The projection of the vector A in the XY plane is the A prime, which is the line over here. So this is our XY plane at the bottom. We can project this A vector, meaning that you shine a light on the top of the A vector the line is parallel to the bottom plane, and it will give you a distance, which is the A prime distance. This magnitude, you can find it by doing the square root of ax squared plus ay squared, which is what we did in the previous video. And then you can find out the total amplitude or the total magnitude by using the A prime with the AZ square. So what is the plane that we are looking at? We're looking at the plane from here to here and from here to here. So this is the plane. We can do the same thing to find out, well, what is the magnitude of this A, which is the blue line here, by looking at this yellow background plane. Where you have the bottom length is the A prime. You have the height to be the AZ. And that will be simply like you do an X and Y if you represent this one like an X, and this one is simply just a Z. Okay, so you're looking, let me put an X plane here, but this is different from the X. So you're looking at this axis, the new axis, the X plane and the Z, and you are doing the same thing to find the magnitude. And that is what this is. And you will find out when you do this, the A prime square simply just this one and take out the 1 over 2 exponent, and you are summing the x squared, y squared, z squared together. Now what about direction? How do we find the direction of the Cartesian vector if we know the components? For the direction of the 3D vector, you have 3 angles, the alpha, beta, and gamma. Where the alpha angle is the angle of the vector with the x-axis, beta is the angle of the vector with respect to the y-axis, and gamma is with respect to the z-axis. To do the calculation, you can use the trigonometry, and these are the equations that you can use. So for the alpha direction, we know when you do the cosine alpha, it is equal to the x component divided by the total length of the vector of A. If you wanted to find out the beta direction, you use cosine beta, and you're going to use y component divided by the total magnitude of the A. When you want to find the z, then you are using the cosine gamma and AZ divided by the total length of the A. So what you need to do first is that you need to find the total amplitude of the resultant vector by knowing the component x, y, and z. Take the square, sum of the square, then take the square root of it. And that's how you do the calculation. So how do we represent the direction of the Cartesian vector? Well, you can use the sum of the unit vector as the unit vector of the resultant force of the A. So this use of A meaning if I wanted to have the vector to be in the same direction of my A vector, but I wanted to make this one only have the magnitude of 1. That is the unit vector of A. This use of A represents the unit vector of the A component of the A vector. It has the same direction of the A, but it has the only magnitude of 1. It doesn't have dimension. It's the dimensionless. So to represent that, you use the vector of A divided by the magnitude of A. The vector of A can be represented as the component. So when you look at these are the vector of A. and you use A divided by each one of the component, you will get a unit vector of A, and which will be these. And if you remember in the previous slide, we show you the cosine alpha, cosine beta, and cosine gamma are the direction that is associated with ax over a, ay over a, and az over a. So it just simply tells you the unit vector has the component of this much and this much and this much in each one of the direction. So what happens if you have two or more three-dimensional forces and you wanted to add them together? We do the similar thing like the previous slide, but we add one more component, which is a z component. You sum the component at a x, sum the component at y, and sum the component at a z, and you multiply with their unit vector I, j, and k. That's how you represent the resultant force in their vector, but in the Cartesian vector representation. If you have subtraction, you minus the amplitude, so it's very similar. Okay, so let's use an example to show you how we do the calculation based on what we just talked about. In this example, you can see there's a hook and there's two cables connect to the hook. And they're in the three-dimensional situation because you can see you have x, you have y, you have z, right? So this x, this is a y, and this is a z direction. You have f of 1 and f of 2. This is the f of 2, this is the cable 2, this is the cable 1. If we apply F1 to be 500 pounds and F2 is 800 pounds, these are the US custom unit system. That means the pound force. And they give you the angle, but the angle that they give you, they don't give you a very straightforward angle. You have to be careful how to look at these angles and be able to find what direction they actually represent. In the f of 1, they have 3, 4, 5, right? So this 3, 4, 5 is represented as the very strange direction. The 3 represent in the z direction, the 4 represent in the y direction. And it looks like the f of 1 is a vector that is on the x and y plane. It doesn't have the z component. It just parallel to the x and y plane. Okay. But for the f of 2, it has an angle between x and y to be 30 degrees. It has another angle that is between the z direction and the xy plane with an angle of 45 degrees. Okay, so the 30 degree is going to be the angle between x and y. The 45 degree represent the angle between the kind of like a z, right? And what else? And the x and y plane. Okay, let's see how we solve this. Let's look at the F1 first. And the F1 is horizontal to the XY plane. It has a 3 in the Z component. It has a 4 in the Y component. So you can think about this just like this one here. This is going to be the new axis. If I wanted to draw a new axis, wait, this is, yeah, this is going to be this axis, and there's nothing in the x component. It's just on this plane, so it has only the y component and only the x component and the z component. Yeah. So f of x is equal to 0 because there's no component in the x direction. You have y direction component, and which will be the amount of a 4 divided by the 5, and that will be 400 pounds. And the z component is going to be 3 divided by 5, which is 300 pounds. And then you represent f of 1 into xyz component. Now, f of 2 is a little bit hard to deal with, and this is going to be the challenge when you are taking the exam. You have to think creatively and look at the things in 3 dimensions. The first thing we do actually is not simply just use 800 to do the computation. You actually have to decompose that into the coordinate system that you can decompose that into the x, y, and z component. So what we are doing here first is that we try to decompose the f of 2, which is this one here, into 2 components, and one is this one here, f2z, and the other one is f2 prime. The f2z is the component of this f of 2 in the z-axis. So this is the z-axis. If you extended this, this is a component. If you project this one to the z-axis, right? So this amount from here, use another color, from here to here. Wow, this is not very obvious. From here to here. Okay. Here to here. Okay. It's the same from here to here, right? We just kind of project that over here. And so what is the angle? Well, the angle is 45 degrees, because here is the 45 degrees. So then you can say this is a 45 degree. These two should be the same because they are perpendicular to each other. And that's 90 degrees. So 45 degrees for each side. And if you know the length of this one, which is 800, you multiply cosine 45 degrees, you got f2 of z. You can also multiply sine 45 degrees, is giving you the same thing. And f of 2 prime is going to be the cosine 45 degree, right? So which you will represent this much of the length, which is the same as this much of the length. Okay, so that's what we have. Let me just clean this one up a little bit so you can see things more clearly. So then once you have these two components and you notice that z is going down, when we have the z going down is going to be negative, and that's why you have negative sign right here. And the other one is going to be positive. Now z component is the component itself, so we don't need to do anything about the f2z. We do need to do some extra work on the f2 prime because f2 prime is not in the x, it's not in the y, it's on the plane of x and y. So we have to do the resolve again to decompose this f of 2 with an angle of 30 degrees at here. You decompose that with the cosine 30 degree to be the fx component, which is this one. And you got the f of y to have that component in the. So this one here is going to be the f2 of x. And then this one here is going to be this one here, the f2 of y. Both are in the positive direction, so this is the positive direction, this is going to be positive direction, so they are all positive. And then you can represent f of 2 in this vector form. So now we have f1, f2, they are all in the vector form. We sum the component at the same unit or sum at the same direction, and you got this final vector f of r as the final resultant force.